So the next presenter, as anticipated by Professor Kappos himself, is Professor Paolo Franchin from Sapienza University of Rome. He will now be starting with more specifics on these regarding pieces of design and data. So Professor Franchin is a full professor at Sapienza University of Rome. Again, a very well-known name, both to myself personally as well, together with Professor Bento, who was also mentioned during Professor Kappos' presentation. Paolo works in the broader field of earthquake engineering with an important focus on bridges, assessment and retrofit of existing buildings, always with a flavor and with a touch of reliability and sound probabilistic basis. He was also, in addition to this, having led the project team for part 2, he was also involved is very much and still involved in the national code of Italy and also in the model code 2020 of the FIB group. So Paolo, please go ahead.
Thank you, Ricardo, for his kind words. So this afternoon I will talk about basis of design and data for assessment within Eurocode 8 part 3 and its relation to other parts. So basis of design is described as Professor Kappos has already shown, into clause 4, and there is a connection with part 1.1 and also with the Eurocode EN 1990 part 2, which is a novel part of EN 1990 dealing with basis of assessment of existing structures for non-seismic design situation. As far as basis of design is concerned, I will talk about what the reference limit state for assessment of existing structures is. Something has already been said by Mr. Kappos. We talk about the reference method of analysis and the safety format for displacement-based assessment, which, as you have already been told, is the reference method for the assessment of existing structure. So we will introduce a new format for partial factors that replaces the former one and talk about the relation of this format with the assessment for other non-seismic design situations. Then I will move to clause 5 and Annex A, which talks about preliminary analysis used also in collecting the data, talking about data for assessment. So let me save time and keep going to the next slide. Before doing that, this is for your record, the versions of these documents I'm making reference to when I say part 1.1, part 2, and so on. These are all inquiry version apart from the formal vote version of part 1.1. Now, basis of design. Let me start by comparison with the part 3 2005, first generation part 3. In what was then chapter clause 2 and now is clause 4, limit states and return periods were defined for the assessment case. So part 305 gave its own definition of the limit states, which is kind of weird. This is one of the inconsistencies that have been removed. Actually, since assessment is not design, which is quite obvious because we cannot rely on global ductility, the significant damage, which the limit state that we, like safety, let's say, that we usually check in view of the near collapse one, to measure safety cannot be checked. I mean, it's not as good a proxy as it usually is for design of new structure. So the near collapse limit state was introduced and emphasized. Nonetheless, as you see here, the definition of the limit state, the national authorities decide whether all 3 limit states should be checked or 2 of them or just one, without saying which one should be preferred. Also, the return periods were defined in part 305, and in particular, they were 2,475 years and 225 years respectively for the NC and the DL. The 475 years is never touched, as you know. Now, in the new part 3 2023, all this has been eliminated. Part 3 refers to part 1.1. You see, limit states are defined in part 1.1. The return periods are defined in part 1.1, What is it? And this is an important statement. If only one limit state is checked, as a minimum, the near collapse should be verified. Now, this is not a shell, so it's not a principle. There are possibilities, as Professor Kappos has already hinted at, to check SD. But in general, this is strongly encouraged because it's the limit state to be checked for existing structures. This is a change. In terms of return periods, we have to refer to part 1.1, as I said. For consequence class 2, let's say ordinary structure, what was the importance class of ordinary structure before, the return period is 1600. It's smaller than the previous one. It's related to the target reliability, which I will talk about later. So this is a reliability index, a target reliability index for limit state and consequence class. And there is an explicit mention of the fact that lower values of this target reliability, for instance, reflecting a shorter residual life. No, we want reliability rather than in 50 years in less years. Is an explicit possibility, decision, of course, by the relevant authorities. So you can differentiate reliability of existing structure with respect to those of new structures. So what type of analysis should be carried out? In general, not the force-based approach. This is immediately ruled out as, let's say, a limited exception, because Q values for the near collapse limit state, which is the reference limit state, are not available. In general, the ductility of existing structure is not even enough to support the Q values for significant damage. So it is permitted, but with Q values that are given in this part, in part 3, and are lower than those for new structure. And the intensity, bear in mind, is the near collapse intensity. So for 1600 years rather than 475 years. So it's larger. When this is going to work and give a positive outcome, possibly in low, maybe in moderate seismic action class, which is where it is permitted. If you find a positive outcome, this is okay. If it's negative, this doesn't mean that the structure is damned, is going to not perform. It may still be compliant, but you have to reanalyze with displacement-based approach, which is the general method. It was put forward as, let's say, an attempt in part 305. Now it's possible also for design for all types of structure and geotechnical systems. You find the displacement-based approach, let's say, at parity of standing with the force-based approach in all parts from 1.1 to 5. It's based on linear analysis, usually static, and in deformation checks for force checks for brittle elements. Of course, you need to have the same safety resulting from the design with the DBA or assessment with DBA than that you will have with the force-based approach. So this meant that the safety format needed to be reassessed. So in this safety format, of course, enters into the checking the compliance, performing verifications. So talking about compliance criteria for compliance are, the first thing that it is said is that existing structure have their own specificity, and they can have different uncertainty with respect to new ones. So it means that you can use different partial factors. So going to verification rules, of course, you see different partial factors means that the reference method is, as usual, the partial factors method. But there is one new item which is quite relevant. It's not going to be used often, but it is a novelty. Annex E, actually not F as in the version I'm referring to, it is as a new number. Annex E of part 1.1 introduce a higher level reliability method, an explicitly probabilistic method for checking the safety. It is not foreseen to be used in 99% of cases, but maybe for a 63B structure, it could be an option. Everything else will be done with the partial factor method, and we have to compare design value of action effects with design values of resistances. Now, focusing on the first one, this factor is something new. It's not new. It's in the formulation of EN 1990, but the way it is used here is important. It is for those cases where you have uncertainty in the modeling of the structure that are related to, for instance, damage due to an earthquake. When you are assessing the structure to retrofit it because it has been damaged in an earthquake, you may not be able to. Of course, if damage is very heavy, and it's easy. But if damage is not that heavy, understanding how much the capacity, the resistance has been reduced might be difficult. So also the response is difficult to assess. you have to amplify response with this gamma SD. In all other cases, so whenever you carry out assessment just because you want to improve your structure, there is funding for doing that, gamma SD will be 1. For resistance, you have the usual expression here from Eurocode 0, and but you don't have the previous, let's say, uncalibrated combination of confidence factor and material partial factors. You have just a single partial factor on resistance, it's called gamma RD outside, that divides the resistance, and this factor accounts for all uncertainty in the problem, meaning for the target reliability, for the uncertainty in relevant variables like those that enter into the resistance model, including statistical uncertainty, because they are usually estimated based on a limited sample size in existing structure, plus the model error, very important, of the resistance model itself, which is, I can anticipate, the largest contributor to the total uncertainty. So we will focus from now on the resistance side, which is where we have this gamma RD factor. Let's go to representative values of material properties. So for existing materials, of the existing structure, this is very important. The properties, let's say, material properties or product properties have to be taken as the mean. Also, this is different from what used to be done in part 3 of 5, as you see. It's not the mean divided by confidence factor and the partial factor. It's really just the mean. And these are the mean from tests of materials, for instance, carried out at the time of assessment, and other sources of information. Let me make a comment about this now. For instance, you are assessing a structure that has maybe 50 years of age, and you have original design documentation in the form, for instance, not of design specifications, but as we will see, I will make some examples later, soon, actually, not much time left. But you have tests carried out at the time of construction. Those tests are tests reporting resistance 50 years ago. No? You should take care in bringing them to current time when you combine them or you compare them with the result of tests carried out now, because there is evolution over time. This is not said explicitly in the code, but it's a general good rule in assessment. So yes, you have to take the mean, but the mean is the mean of values that first need to be made homogeneous. This is just a relation from the FIB model code, which tells you how to do that for concrete strength. This is a very important step forward, because the same values of material properties go into the verifications, into the formulas for resistance using verification, and into the model. So the model is not just linear elastic, it's a nonlinear model. It requires resistances. You don't need to compute the resistances twice. You compute them for verification, and in that case, you divide them by gamma to account for uncertainty, and you put them in the model. This is, of course, less error prone and goes towards ease of use. The second thing that this text says is that different mean values may be used in different areas of the structure. This is very important because before you could not do that, but it is often the case that because structures are cast in sequences, I'm always referring to reinforced concrete because I'm more used to reinforced concrete, but this also applies to other materials where you can have different homogeneous portions. You can identify different homogeneous portions in the structure, maybe through non-destructive testing, and then go and assign different mean values to the material properties in different portions of the structure. This is also something that came out of applications and is very important. Look also at the relation, the relatively good relation, which is between non-destructive testing, in this case SONREP test, and destructive testing. This is important for material testing. I'm going to talk soon about. One important thing that you have to do is that when you carry out tests, you also have to compute the coefficient of variation, let's say, of these tests. For instance, values of concrete strength, of steel strength, and report it. This is important because it's easy to do, just computing a coefficient of variation, but it allows to compare with values that come from a lot of applications of the previous code or similar national codes, and this part 3 or 5 like national codes. And this is important because if the standard deviation of the natural logarithm, let's say the coefficient of variation that you find is very large, larger than the reference values, this may, you know, ring a bell and say there's something wrong. Either testing is unreliable, repeat it, check better, or this is an index of poor construction quality. So take extra care. This is said explicitly now. Then you have, now going back to materials, materials are divided into 3 categories, classified in existing, added, and new. Both added and new are new material. It's something that you add to the structure, but the distinction is important because this added material is new material used in retrofitting a member, like the concrete in a reinforced concrete jacket around the member, while new material are new material used in a new member, like, you know, the steel in an exoskeleton. Basically, in all cases, you can use, or you should use, the mean as a representative value for existing material, as we have seen in the previous slide, for added materials, and even for new materials when they are built, they are used to build members that, let's say, work in parallel with the structure. There is one exception, which is the one I'm showing here. Here something went wrong. No, okay, sorry. So yes, something is missing here. I'm sorry, but you are using, let's say, the usual characteristic values for the material to make your verification when the structure, the new structure, is built in parallel to the existing structure and is meant to carry the entire seismic action. So in that case, really what you're doing is you're building a new structure and you are checking it as a new structure. So it's like you are applying part 1.1 and the other parts. So this is, Professor Kappos already said this. The mean is used, let's say, almost ubiquitously here. And this goes along with the nonlinear analysis, because you can, as long as the analysis is nonlinear, this is going to give you an unbiased estimate of response. It's better to use the mean. This was an aspect that took us a lot of time, let's say, in the interaction with the Eurocode 8/1990, because and Eurocode 8/1990 said explicitly now, it says explicitly that using the mean or the characteristic value as a representative value of a property in the verifications has no effect on safety. They are both equally valid choices. This is recognized now. Of course, since what counts, what matters is the design value. If you use the characteristic value, lower fractile, you will divide it by a given partial factor. If you use a mean value, you will divide it by a different partial factor, usually larger. So as long as the partial factor account for the fact that you use the mean, and I can tell you part 3 has partial factors that account for this, then there is no effect on safety. No problem with that. Of course, you can come up with partial factors that are larger. So the last important point I have to say here is now how these partial factors have been calibrated. So let's say calibration of partial factors is an optimization problem. This is just for reference for you. Okay, this is not what has been done in the Eurocode. Usually, what you do is you choose a set of partial factors. You consider a number of design cases. You evaluate, given the partial factors, you know what is the resistance of the structure through the design equation. And you can compute, given effect and resistance, the reliability of that design and see whether it is far from the target reliability. You sum up all the target, all the deviations from this target and repeat until you minimize. And you find the partial factors that minimize the discrepancy between reliability of the structures and target reliability for all design cases. So the Eurocode use a simpler alternative, which is called the design value method. This was used also in the older Eurocodes, but it was not explicitly. You only got the results. For instance, gamma C equal 1.5, gamma S equal 1.15, and so on. They were calibrated with this method, the design value method, which is a method that basically has a closed form for the partial factors as a function of the target reliability, you see, beta T, and of other things. So now, since the problem of calibrating new partial factors for the case of assessment is not just part 3 of Eurocode 8 problem, is the problem also of other non-seismic design situation where you need to carry out assessment. Now Eurocode, for instance, Eurocode 2 for concrete in an annex gives this method, this expression for the partial factors, which is, I'm telling you, the same used in the case of Eurocode 8. So this is the new format of the partial factors. Now, in this format, you have these coefficients, which are called alpha E and alpha R. These are the sensitivity to the load and the sensitivity to the resistance, which are a function of the uncertainty in load and resistance. Now, uncertainty in load and resistance are changed from case to case. The reason why this method was used in the Eurocodes is that in 1982, someone, Professor Koenig and Hosser, came out with this, many of you that deal with assessment might know these values, with these famous values for alpha E and alpha R for non-seismic design situation. Well, what we did during the process of revising part 3 was to come up with new values specific for the seismic case. These values are different because the weight of the seismic action with respect to the resistance in the seismic case is different from that in non-seismic design situation. And in particular, in the seismic case, the action effect is more important than the resistance. Okay? So there were some seismic specific developments. So these are, just for documentation. If you see the slides, the PDFs, this is the uncertainty in the action, and it accounts also for record-to-record variability, all things that are now, by few years, quite a few years, well known. And what we added also, very important, is the uncertainty resistance. The uncertainty resistance is the composition, let me show here on the graph, of the uncertainty of the resistance model and the uncertainty of the input variables. But what I'm showing here with this drawing is that it is always more important the uncertainty of the resistance models. The problem is that we don't have perfect models. And this is just an example. For instance, if you're checking with the displacement-based approach, a beam or a column for inelastic rotation, you have a model for inelastic rotation. This is the theta ultimate plastic part, or the total ultimate rotation. And you have a predicted value and experimental value. Now, all models in the Eurocode are unbiased, means that they have a ratio of mean or median experimental to predicted almost 1. These are two examples, one from my colleague Dimitrios Lignos here about steel, and this is about concrete. It comes from the school of Patras. You know the models. Well, they have different coefficient of variations. These coefficient of variations are reported here, and these are you see that they are so large that they dominate the total uncertainty, which is the uncertainty accounting for the uncertainty in the input variables to these models. I'm not showing expression here. There is a representation on concrete later. So, final important thing to know is that since Eurocode 8 does not use a partial factors on the load side to amplify the seismic action effect, all this has been turned into a single partial factor format. Okay, and with the value that is 0.85, that accounts for uncertainty on both sides. You need the target reliability, and the target reliability is given in Annex E of Part 1.1. These are target reliability index in 50 years. I'm not saying how these were derived. This is something from Part 1.1. And if you consider, for instance, consequence class 2 and near collapse and theta ultimate, you come up with something like this. These are values for new RC members. Okay. Please, I'm not showing values for existing members because this may change as part of the process of replying to the inquiry phase, and so they are not final, while those in Part 1.1 are already final. So these are the values for the new structure. For an existing structure, gamma D depends on the knowledge level. This is already the terminology used in Part 1, in Part 3, 2005, and there will be larger than 1.55 in this example for similar reinforced concrete member. There is a trick for this to work. To use just one factor and to eliminate the second factor, you have no gamma E, gamma R, but just one gamma R. Then you basically need to target the return period of the seismic action to the target reliability. So this is what people in research are calling risk targeted seismic action. This is exactly what is in the Eurocode now. This is for part 1.1, but it's used in here, so you need to know that. And these are the return periods, and these return periods correspond to this target reliability. Now, I see that I'm left with very few time here, so I apologize. I will talk quickly about sources of data for assessment. Now, there are two types of sources: structure-specific information and relevant generic data sources. Now, relevant generic data sources may provide very useful information, especially in an initial phase where you need to fill in information that you still don't have. In case of conflicts, of course, structure-specific information is always the one to be relied upon. The data are listed in 5.2, the data you need to get for your structure. But one specific aspect that is very important is the history of the structure. This is usually very important considered very important for historical structure, like heritage structure is always important also for structure in reinforced concrete, for instance, because they may have gone under changes. And these provide information, especially about this, about seismic design criteria and level of seismic action used for the initial design. No? So this type of information, where to go to look for generic but relevant data sources, is a matter of knowing the history of the structure. So I'm over time from now on, I will go even faster. This is an example from a paper studied here of relevant generic data sources in terms of design procedures, material properties for Italian reinforced concrete structures. And what I want to say here is that this information is very local in space and time. So you need to know in every decade or so what was the code, what were the materials, and in each area, and in Germany, in France, in Portugal, or Greece, or Italy, or so on, it will be different. So these ideally will go into the national annexes. This is work for the NSB, National Standardization Bodies. This is just an example to say that you may find within your structure portions that are from the 1200s. This was a case we had to look at, from the 1800s to different types of masonry, and then this was emptied and filled with reinforced concrete from the 1940s. That certainly is not code conforming reinforced concrete from today. So this is the type of things you need to know to define also homogeneous areas to carry out your inspections. No? And this is another example. This is an airport in Italy, and it was built through, as you see, 8 different stages, starting in the 50s and ending in 2010, and all different codes were used along the way, and materials. So all this information goes to boxes, which are geometry, details, and materials. And these are the same as in part 3. What is different, but Professor Kappos already said that, is that now you don't have a unique knowledge level, but you have a knowledge level for geometry, one for details, construction details, and one for materials. Each with its own distinct level, and each with its own distinct level in different portions of the structure. The concept here is very important, is that having a lot of information on a portion of the structure that does not really change the result of the assessment, for instance, your structure is going to develop a first soft story, is useless. You should not investigate or spend energy or do invasive testing in areas of the structure that do not matter for the final outcome. And this is now possible, what it was not possible before. So, for instance, geometry, you need to use structural drawings rather than architectural drawings in order, so you need a survey if you don't have the drawings. You have this general kind of table to establish what is the knowledge level in geometry that you reach. And you see, you reach the maximum level of, it's called high, no? It's not called complete as before because it's never complete, it's called high. KLG3, if you have the complete set of drawing and you still perform a limited check on consistency of the drawings with reality, or you have incomplete set but you do an extensive survey, or you don't have drawings but you do a comprehensive survey. It's not moving. This I can skip. What do we mean by limited, extended, or comprehensive survey? It is the percentage of elements P that you are going to investigate per each element type. And this percentage is given by this formula. This is a change with respect. So these percentages are given by a formula, and they are not fixed as they were before. They depend on structure size, and they decrease with structure size. This is important because saying 20% on a structure that is very large, it means a lot of test inspections that are not really used or useful. You get good knowledge with maybe a few tenths of elements. You don't need 100. But with large structures, this was a problem. So now you see, this is the number of tests you need, of elements you need to inspect, M, percentage times M, with N increasing. And you see that you never go to the number of elements you need to inspect is always, I didn't show the one you got before, is always lower than the one you needed before. Of course, you need to be smart and also serious, and not to let's say exploit symmetry or other conditions like this or accessibility. You say you may have an easily accessible set of members, but they are all the same because of the design, and you can tell that. So you don't want to go and inspect those to satisfy your probability, your percentage requirement. You need to inspect different elements that are in different positions, so that you can extend those and maybe go beyond these percentages that you see here. So this is a warning that is very important. Preliminary analysis. It's carried out after. It's not mandatory. It's encouraged. It's a displacement-based analysis with nominal properties, and you will go and see that. Let me just do a comment, and I'm sorry because I'm late. I cannot stay more on this. The idea here is that you identify with the preliminary analysis that you can do, because you can set up a model just with geometry by assuming properties, and you can estimate in a let's say simplified way the capacities. You identify areas where the demand is going to be, in terms of relation to the capacity, larger. These are the areas where, if you carry out this analysis, you can focus your test, reducing the overall effort of inspections and testing the structure. So here, this is just for talking about details. Just a warning, this is a destructive test. This is a non-destructive test. Some information you can certainly see, because the stirrup spacing is something that you can see from a non-destructive test. It's more difficult to see certainly the diameter, but you can calibrate this with a few exposures and then use more non-destructive testing. And this is exactly the principle. So this code now, let's say, trades part of the destructive testing with a larger proportion of non-destructive testing in order to reduce the invasiveness of the test to carry out on the structure. In particular, for materials, destructive testing is always almost always possible to avoid for masonry and timber, where I'm just reporting some example here for masonry. It is much more invasive than it is in concrete, where, for instance, sorry, these are the details. It's later, where you just take cores or portion of steel. It's less invasive than in these cases. So I'm just showing material specific precision over reinforced concrete, but since there is a presentation of this later, I will just limit to this comment. One thing that you cannot see with the non-destructive testing is lap splices, because you won't be able to see the length of the lap splices. Professor Kappos has already shown it. This is reflected in the This is reflected in the models of deformation capability, where if you don't know, you see, the lap splice length, you are forced to presume that it is lower than needed, and you need to use a deformation capacity that is affected negatively, detrimentally by overlap length. So these are few things new in Part 3 that really affect the outcome and forces you to go and, for instance, go and make your inspection here, which is not as easy to do as midway, but mid-height, no? But is where you really need to go and look, because that's what is affecting the deformation capability of these members. Rita, I think I can go quick on here. This is not needed because really this is material specific provisions. So something that will be talked about by a colleague later. I apologize. It took me really too much time on this. So let me go to the conclusions. You will see the PDF on this. So near collapse limit state, strongly encouraged, almost mandatory. Return period linked to target reliability, 1600 years, not 2500 like before. The reference method for analysis is displacement based. This means nonlinear static analysis. Mean values are used everywhere for both the model and the verifications. And there is a single partial factor, gamma RD, that depends on the knowledge levels. The knowledge levels are three distinct for geometry, details, and materials. And it is possible to achieve good knowledge levels in specific parts of the structure if you focus the test there, limiting the effort somewhere else, based on preliminary analysis, which is a simplified new introduced analysis that helps you identify in this area. Destructive tests are limited, and there is a preference for a larger proportion of non-destructive testing. So and finally, the total number of survey sections, details, and material tested increases less than linearly with the structure size with the new formula for the percentages of test. I'm very sorry for having gone over time, and I stop here.
Thank you very much, Paolo. Although we are 15 minutes behind schedule, I think we will still take one question so that at least we have some interaction with the audience. I will choose a question that was raised by two of the listeners. So by João André from the National Laboratory of Civil Engineering in Portugal, and Ciro Canditone from the University of Naples in Italy. So their question is, will Eurocode provide modeling guidance, which materials models to use and how to determine their parameters, discretization and type of elements, or numerical algorithms and sensitivity analysis? So they believe this is very important given the emphasis on nonlinear analysis.
This is more of a guideline than of a code thing, so you should go to a commentary, but I should not be the one to answer. I know part of the answer. I think you can move on to the next presentation and they will have their answer, because this is what is written in analysis. For instance, there is some guidance on the, but I don't want to, this is something a colleague is going to say right after me. I'm sure they're not going to be disappointed. There is some, certainly, there is some guidance, not complete.
Okay.
The next presentation is going to answer this. There are examples of constitutive laws and so on.
Okay, and the same person asked a question related to sigma R. So was sigma R calculating using models that cover an extensive amount of simulation practice?
Yes. Tens of thousands to thousands, depending on the model. This is in the background document. Yes. I understand the question. The sigma R are averaged over a very, of course, they are carried out for all the models, the resistance models. And for each resistance models, like a kind of a design space was created covering a very large amount of. And in any case, as I've shown, what is more important always for these models is the error in the model rather than the properties of the input variables that enter into the model. They are not the dominant. So since the design space is going to affect that, you understand that it's kind of a minor, not expected, but in practice, it's not that important. Which is also the reason why the partial factors gamma, RD, and KL, as they will see, users will see, are mildly dependent on the knowledge level. And this may not, you know, when you calibrate them correctly, you understand that that's the truth. Okay. This is also the reason, Ricardo, this is also the reason why, for instance, it is more important to achieve a KL in order to use a different model. For instance, if you do not look at the overlap length, because you do not uncover overlap length and you do not check it, you are forced to use another model. It's not really what makes the difference, the gamma that you put on the model, because it's the model that is penalty for you.
Of course. Okay, thank you very much. Paolo, if you
That's
don't
really
mind, stop sharing the screen. We will move to the next presentation.